Okay, Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Okay, so we will continue our lab practice session. Okay, regarding CFD. Okay, flow analysis, which is including the thermal or heat analysis. Okay, so you already learned how to run the flow analysis using the Hyperwork CFD. Okay, you already learned how to set up the model, how to define the inlet, outlet, material, okay, meshing, okay, and to evaluate the result of the flow analysis. Okay, so now we are doing the uh, heat analysis, okay, for the same example of the mixing elbow. Okay, so first step, you need to open up the Hyperwork CFD. Okay, so this is a Hyperwork CFD software, and then you go to the file. Okay, you go to the file, you open up the HM file. Okay, Hypermesh model, you click on that, and then find it the HM file of the mixing elbow heat. Okay, and click open, and it will open it the mixing elbow. Okay, the same like you do the flow analysis for the mixing elbow, but for this we are purposely to run the heat analysis, which is we want to focusing on what is the behavior of the mixing elbow or this pipe, focusing on the temperature. Okay, focusing on the temperature. Okay, so for the first step, you already uploaded the model. Okay, and then first step, you need go to the flow. Okay, you need to define first the setup simulation model. Okay, setup simulation model, you click on that. So this is a setup simulation model. We have a time. Okay, time, we have a two different type, which is a steady state and also transient. We still on the steady state behavior. Okay, you choose a steady state, and then you go to the flow. Okay, flow, we also use by default it's a turbulent using the Spalart Almaraz. Okay, you use this default parameters. Okay, and then you go to the heat transfer here. Okay, below the flow you have a heat transfer. Okay, by default it's not checked. Okay, it's not click check here for the heat transfer. So if you want to run the thermal analysis or heat analysis, you need to tick the heat transfer here. Okay, and then for multi-fluid we don't have any analysis for multi-fluid. And then go to the solver control. Okay, solver control, so make sure this activate active equation, we have a tick for the temperature. Okay, for only for the temperature, don't need to tick for the thermal flow. Okay, you just by default steady update factor, you just use this default value, and also the steady maximum step, you just put the default value. Okay, so you're already setting up the simulation setting. Okay, you just close this, and then next is we want to assign the material. Okay, we want to assign the material. So before that, for the thermal analysis here, okay, before if you remembered, for the flow analysis you just define the fluid. Okay, you just define the fluid. So the fluid is just in the inner wall. Okay, just in the inner wall. But for the thermal analysis, you need to define the fluid at the inner wall here. Okay, the fluid flow here, and also the wall. Okay, the steel wall here, you need to define the material also. Okay, so in the material you don't have any properties of the steel, so you need to assign, or you need to create a new material for the steel. Okay, you go to the material library. Okay, material library, for the fluid you have a solid here, just only have a stainless steel, but you don't have any solid steel. Okay, so you go to the my material, default solid material, we have this, and also the aluminium. So I need to create the properties material for the steel. So you click on the my material here, and then you click add. Okay, you click the plus icon there, you click add, and then you need to define the properties of the density of the steel. So you fill up with the value of 8030, okay, for the constant density here, and then you need to fill up the value of the specific heat for the steel. Okay, you choose the type of it's a constant. The value of specific heat is 500. Okay, and also you need to put the value for the conductivity. Okay, the value of the conductivity is 16.2. Okay, so you can get this value from the material properties from the other webs. Okay, for the steel solid. Okay, so if you already fill up the all these three parameters, you just close it, and then you have this here. Okay, name is it's a solid. You can change the name to the steel. Okay, steel. Okay, so steel density is 8030, specific heat is 500, and thermal conductivity is 16.2. Okay, so you already create the new material for the steel. Okay, for the fluid you already have a in the library. The properties you already have in the library, so you don't have to create the properties of the water or fluid. Okay, so you close it, and then next you need to assign the material for the inner wall here. So inner surface area here for the fluid, and also for the outer surface here is a steel. Okay, it's a steel. Okay, so you click on the material here. Click on the material here. Say first we want to assign for the fluid. You click on the inner surface here. Okay, you can choose as a water. Okay, water. So you click on this icon. Okay, the arrow icon here. Okay, so this is a fluid or water, and then you click on the outer surface here, and you choose as a steel. Okay, steel, and then you click on the green tick here. Okay, so for the material you already have a sign for fluid, and also for the outer surface is a steel. Okay, you already assigned with the um material. Okay, next we want to assign with the inlet and also the outlet. Okay, so you go to the profile here. So profile icon, we want to define the inlet. Okay, we have a two inlet here, the same like a flow analysis. We have a small inlet here, and also the bigger inlet here, and also at the top is a outlet here. Okay, so first we want to define the bigger inlet here. Okay, you click on the profile. Okay, you click on the profile, and then you choose this for the bigger inlet. Okay, and you set the average velocity is a uh, 0.4. Okay, 0.4, and we have an icon for temperature. Okay, we have an icon for temperature. We need to set the temperature value for the bigger inlet, which is you need to uh, put 295. Okay, for example, 295 is a temperature that flow in the bigger inlet. Okay, just click, and then you click this icon. Okay, so you already assign the properties for the inlet, and then you go to the small inlet. Okay, small inlet here, you click on that. Okay, the average velocity for the small inlet is 1.2. Okay, 1.2, and for the temperature is 320. Okay, 320. So you click on the green tick here. So okay, you already assigned the, we have a two inlet at the boundaries. Okay, inlet, the bigger inlet, and also the small inlet here. Okay, so next we want to assign the outlet here. Okay, assign the outlet. Okay, you click on the outlet icon there. Okay, you click on the surface, top surface of the outlet. Just give a by default value 0 for static pressure and also pressure loss factor, and then you click on the green tick here, and you already define the outlet. Okay, so we already finished assign of the inlet and outlet. So next step, we want to set the symmetrical plane. Okay, symmetrical plane, same step like flow analysis. Okay, so you click on the symmetry plane here, symmetry icon there, and then you choose here. Okay, you choose this for the symmetrical plane. Okay, you click on that. So this is the first symmetrical plane. Okay, and then for the thermal analysis, since this is the fluid flow, and also we have a solid steel here, so you need to define the pipe wall or steel wall symmetry. Okay, yang before this symmetry is for the fluid. Okay, for the fluid, but you need to define the thicker wall for the symmetry. So you need to click on this again, define symmetry condition. So okay, the green one is you already define the symmetry for the fluid, okay, or the inlet or the inner wall, okay, but you need to define the outer wall here. So you need to click on the blue one here. Okay, okay, first surface, the second surface, and also the third surface here. Okay, so you need to set for the three surface, the first surface here, the second surface, and also the third surface. And precedence you set as a 1 for default, and you click OK. Okay, so basically we have a two symmetry plane here for the inner fluid and also for the wall. Okay, for the wall. Okay, we have a two symmetry plane here. Okay, next. Next, we will need to set the boundary condition for the outer pipe wall. Okay, for the boundary condition. Right. Okay. Okay. So next, we need to define the boundary condition for the outer pipe wall. Okay. Since this is a solid wall, okay, the steel wall, we need to define the boundary condition for this or the temperature for the pipe wall here. Okay, pipe wall here. So the boundary condition, you can choose the no slip. Okay, because we don't we define the wall is no slip condition. Okay, no slip wall condition. So you click on the no slip here, click that, and then you need to choose the outer surface here. Okay, we have a we have a four surface here for the outer wall. Okay, you click first, second, third, and also the small one, fourth. Okay, so this is the outer surface here. Okay, okay, and then we need to define this. Okay, we need to define near wall treatment. We have a wall function here. Okay, wall function. This is a remain by default. Okay, and then you click on the temperature. Okay, the temperature here is the thermal boundary condition is a flux. Okay, and then you need to put the convective heat resistant. Okay, heat resistant temperature. Okay, value to 302.954. Okay, this is a value for the heat reference temperature. Yeah, convective heat reference temperature here. Okay, convective heat reference temperature, you put the value of 302.950, and the convective heat coefficient you put as a 100. Okay, as a 100 value. Okay, so this is a boundary condition for the wall. Okay, no slip wall. Okay, so means that the wall can resist the temperature about 302. Okay, with the heat coefficient about 100. Okay, you click OK. So you already apply the boundary condition here. Okay, the boundary condition. Okay, next, before we mesh, okay, before we mesh, we need to define the refinement zone. Okay, basically, for the flow analysis, actually, we need to define the refinement zone. What's mean by refinement zone? Refinement zone means that you need to identify in which area is a critical area. Okay, critical area, which means that the flow and in that area is a very critical, which is the very high flow there, or very high heat temperature occurred at that area. So you need to define first. Okay, basically, I already missed this step in the flow analysis, so you need to do that the same step procedure in the flow analysis and also in the heat temperature. So you need to define the first one is the refinement zone. Okay, the refinement zone, and also you need to set the boundary layer control. Okay, so the boundary layer control. Okay, first step, we want to, before we mesh using the batch mesher, we need to define the refinement zone here. Okay, in this part, okay, the critical area is in this area. Okay, in this area, which is a very high velocity here in the small inlet, and also the area is very critical. It's very small, but the flow is velocity is very high. So uh, the flow, you need to refinement mesh here, so that it will calculate the flow, the thermal in this critical area is very accurate. If you are not refinement the meshing in this area, maybe your result will become it's not so accurate. Okay, it's not so accurate compared to you refine this area. Okay, how to refinement the meshing area? First, you need to go to the mesh. Okay, so mesh, this you can use this function here. We have a zone. Okay, this is a refinement zone area, and then you can use the boundary layer, so to create the boundary layers, and also the surface, set surface mesh control. Okay, define surface mesh size. Okay, first, okay, since we already defined this area, okay, the cylindrical area, okay, this tube area is the critical area, so you need to define the critical zone area or the refinement zone area. Since this is a cylinder type, okay, it's not the, in the fully assembly is a cylinder type, so you need to choose this icon, which is a cylinder. If it's in a box or rectangular pattern, you need to choose the rectangular, but in this case it's a tube, so the shape is a cylinder. Okay, so you click on the cylinder here. Okay, you can change the view here, so you can click on this center. Okay, click on the center. Okay, we have a parameters here actually. Okay, in the refinement zone here, you already find the cylinder, you right click edit. Okay, so in this we have a refinement size. Okay, refinement size you set as a 0.002. Okay, and you set the radius. Okay, radius, yeah, that we set is a bigger than this radius. Okay, radius. So in this case, you set as a 0.03. Okay, 0.03, and the height is a 0.207. Okay, okay. So you need to since it's back here, you need to change to the other side. Okay, to other side. So negative 0.247. Okay. Okay. So you put this value. So it will create the cylinder. Okay. The cylinder in this area, in this refinement area. Okay. You will see the different meshing will be create at this area. Okay, so if you see this, it's already like this lah. Okay, okay, it's already like this. Okay, so this is we already set the refinement zone here. Okay, next we need to define the uh, surface mesh control. Okay, surface mesh control. You click on this. Okay, the function of the surface mesh has control. We already define the size of the meshing setup. Okay, so you need to select all the surface. Okay, all the surface here. Okay, you need to select all the surface. And so the last one, surface. Okay, so I already set all the surface here. Okay, all the surface in the part, in the mixing elbow part, and also I set the average element size is 0.003. So this is a minimum average element size that will be meshed. Okay, and we set by default with the size factor, geometric feature angle, and the mesh growth rate. We use the default value. Okay, you set the default value. You click on the OK. Okay, so at the setup browser here, we have a surface mesh control here. Okay, if you edit, so dia ada kat sini lah semua. Okay, okay, and then next, before we set the bash meshing, okay, you need to set the boundary layer control. Okay, so at this critical area, okay, I need to create layers. Okay, so layers means that at this area, okay, we set layers so that uh, the value for the flow or the thermal will be captured accurately. Okay, for the layers. Okay, for the layers. Okay, you choose the boundary layer here. Okay, for the boundary layers, we specific on the outer pipe only. Okay, it's not for the fluid, because the outer pipe we set at the solid part. Okay, we set at the solid part. Okay, you set for the four surface here, and the first layer thickness you set as a 0.0005. Okay, and the total number of layers we set as a 5, and the growth method you choose a constant. Okay, so for the growth rate we set as a 1.2, and the termination policy you set as a truncate. Okay, and then you click OK. Okay, so after you set the refinement zone, surface mesh control, and also the boundary layer control, you can start to mesh the mixing elbow. Okay, after you complete the set the refinement zone, the surface mesh control, and also the boundary layer control, so you can start to run or to create a mesh using the batch mesher. Okay, you click on the mesh here, and also you click for the batch mesher here, and also you choose a surface plus volume mesh. The average element size is 0.03606. You set this as a by default. Okay, all this value you set it by default, and then you can click on the mesh. Okay, And then you can see the different when you set the refinement zone and also the mesh control here. So what how about the meshing at the critical area or refinement area? Okay, we can see it. Okay, after you complete the meshing here, so you can see, you can zoom. Okay, so this is a refinement zone here. Okay, what you do for the cylinder, okay, refinement zone for the cylindrical, so it will create a refinement meshing here compared to the other area, okay, that not set with as a refinement. Okay, so you will see the cylindrical area, the meshing size will be smaller compared to the other area. Okay, so there's a difference between you set as a refinement zone or not. And also the boundary layers. Okay, you set the boundary layer control here, you set as a 5. Okay, you set as a 5, so it means that it will create the 5 layers. Okay, 5 layers as a refinement. Okay, as a small meshing size element. Okay, so you see, we'll see first layer, second layer, third layer, fourth layer, and the fifth layer. So this is all what you set before this. Okay, the boundary layers and also the refinement zone. So it will when you run the flow and also the thermal analysis, it will consider this is a critical area and it will see the result. You can see the result is very accurate compared to if you don't set the refinement zone and also the boundary layers control. Okay, after you set up the machine, okay, so you can your model is already set for the run CFD thermal analysis. Okay, you can click on the run here. Okay, you can use the problem directory, mixing elbow, accurate path, processor run. Can put all, okay, serial, and then you can run. And we can see the result. Okay, to analyze the result. Okay, so we already finished run the analysis. So you can right click here and choose the visualize in AccuField view in order you to evaluate the result of the heat thermal analysis of the mixing elbow. So you click on the visualize in AccuField view here. So it will open up the AccuField view to see the result of your file. Okay, the result of your file. So here is um, the result. Okay, you can choose it. The first one, we need to see the temperature first. Okay, we need to see the temperature. Okay, here is a panel for the boundary surface. Okay, for the boundary surface here. So this is your result. You click first. You click the you untick the show mesh, and then you choose the scalar here and choose the temperature. Okay, choose the temperature here. Okay, the temperature, calculate, and also it says for the symmetry. Okay, okay, just symmetry. or you can choose all. Okay, all is battery. Okay. So this is a value for the temperature here. You can see the value. You can go to the legend tab here, show legend, and then you can change the color. Okay, you can change the color here, the color map here. Okay, so the temperature is from 294 to 320. Okay, so the maximum one here is 320. Okay, for the temperature here. So the highest temperature occurred at the small inlet. Okay, the small inlet compared to the large inlet, and it will go to the higher the low temperature. It's not the low one is at the small inlet. The middle temperature will go to the outlet here. But you can see the critical area here is at the small inlet, because we have a high velocity there, and also the temperature, highest temperature here. Okay, and then you can see the velocity. Okay, if you want to see uh, the temperature for the wall, okay, you can create another ID here. Okay, you can create another ID, temperature for the wall. Okay, for the wall. Okay, for the wall, show legend. Okay, the same. So this is the temperature for the wall. Okay, this is the temperature for the wall, and you can see the velocity. Okay, velocity. You can hide first the temperature for the wall. You can see you can use the velocity magnitude. Okay, calculate. Then you can choose all. Okay, so this is a velocity magnitude. You can see the legend. So velocity magnitude is about 1.473. Okay, and you can see the vectors of the velocity here. Okay, the vectors of the velocity here. Option. Skip 7. Head scaling 0.5. Scale 2. Okay, so this is the velocity magnitude here. Okay, you can see the highest velocity magnitude occurred at the small inlet. Okay, so you can see the first one is a temperature. Okay, the temperature one. second one is a okay. So this is a temperature for the in the fluid. This is a velocity magnitude at the fluid through the wall. Okay. So this is the simple basic how you want to evaluate the result for the thermal analysis. So hopefully you can try it at your own using the hyperword CFD. Okay, so thank you very much. Assalamualaikum warahmatullahi wabarakatuh.